Okay, we are live. Assalamu alaikum, everyone. Welcome once again to today's exciting topic. Today's conference is titled Large Reasoning Models, and we are pleased to welcome our host for our speaker for today, Massinissa Abboud. He is an AI developer at SAP and master in artificial intelligence at University Gottazu. Massinissa, we are honored to have you with us. The stage is yours.
Thanks. Thanks. Hi everyone. So, as Mohammed said, we're going to see together a quite interesting topic about large reasoning models. So, if if you're using LLMs or what you consider LLMs in your daily life, there is a high probability that you've switched a long time ago to using large reasoning models instead of just using plain LLMs. So if you're using, for example, the latest versions of GPT-4, they're mainly large reasoning models and not just large language models. And we'll see together what are these reasoning models and what differentiates them from classical LLMs. So before diving into the subject, I will ask you to solve this riddle. So you have 5 seconds. You have a bat and a ball. They both cost $11. If I tell you that the bat costs $10 more than the ball, how much does the ball cost? So you have 5 seconds, and if your answer was $1, so unfortunately you're wrong, because if you do the math, if the ball is $1, the bat $10 more, it means that it's 11, and the total is 12. And the correct answer is, in fact, it costs 50 cents. And now when you do the math, when you add everything, it sums to $11. So I think that if you didn't solve this problem before, you might have got it wrong. And why did you get it wrong? It's because when we are presented with this type of problem and we are asked to solve it in a short amount of time, we trigger in our mind what is called fast thinking or system one thinking. And how does this system work? It is designed so that it gives rapid, fast answer and without really thinking about it. And if you will compare it to what we call a system two system, which is more of a slow thinking system, there is more thoughts that are being made and more reasoning that are being made in general. How does this relate to our subject? We talked about the difference between LLMs and what we want to be large reasoning models, and this is one of the things, because LLMs are a bit similar to our system one thinking or fast thinking, because the way that they're being trained and the way that they behave, they're designed to give fast answers without really thinking about it. And what we want actually to achieve is build models or systems that are able to perform more complex reasoning and think more about something before giving a direct answer. So this is the agenda for today's talk. So we'll begin with some introduction into giving some backgrounds on LLMs and reasoning in general. We'll then dive into how we can actually train these reasoning models. We'll see then the test time scaling, or how can we use them during inference. We'll then see together a live use case, for instance, DeepSeek, that I believe you all heard about the model and maybe tried it yourself. And we'll end up with talking about some challenges and limitations that these models have. So let's begin with some background on LLMs and reasoning. So I believe you're quite familiar now with what an LLM is. If you don't, they are just neural models that are being trained to predict the next token or the next word, given a query or prompt. They are built on the transformer architecture that is well known now. And basically they are trained on a lot of data. So you can imagine everything from the data available online, the data in books, the code, and this is what gives us current the models that are capable of doing many tasks. You are probably using it, for example, to generate some text. You can perform what we call in-context learning, translation, summarization, and etc. So here, yeah, you got the transformer architecture. If you're not very comfortable with it, it's fine. You won't really need to understand how this works in order to follow up this course. But it's something that is quite interesting to study on your own, because sometimes you will need much more than just prompt engineering in order to do your work. So how do LLM learn? So usually we do have two phases for the training of LLM. There is what we call the pre-training, phase, and it's basically the task where the step where we train the model on a lot of text data. So as I said, we give a lot of maybe all what is available online, from the textual data, from data on books, etc. And in this stage, the model learns to identify some patterns related to language. And based on that, what we will then do, and also this is unsupervised in terms of we are just giving a lot of data and we're expecting the model to understand how it is structured, etc. And this gives us what we call foundation models. So if you're using even the earliest versions of ChatGPT, they are not foundation models. They are what we call instruct-tuned models, and they're basically models that are being what we call fine-tuned in order to be able to hold the conversation with a human. And in this fine-tuning phase, we got what we'll do related to, for example, aligning the model output to human preferences. For example, it can be the way the answer is structured, or even, for example, using a set of words that are better or a style that is better, etc. We can also tune the model to follow some instructions so that it gets better at doing a specific task. And it's also related to specifying the model into a specific use case, or maybe also adding some specifications on the output format. And after training this model, we got in the inference phase. And in this phase, you're basically using the model and not training it anymore. And it's basically what you're doing by chatting with ChatGPT, for example. You do some prompting or in-context learning or many other applications. So regarding reasoning, so you might ask, what is reasoning? And it's actually everything that involves giving some thought to a problem. For example, we got abstract thinking, for example. If we got back to the riddle that we saw at the beginning, it triggers some abstract thinking or thoughts that you need to do before solving the problem. And in general, when we talk about math problems, we're usually performing abstract thinking. You got also step-by-step logic. Also, for example, in math, when you have to solve a complex problem, you will do some step-by-step, which is quite easy to understand. You got also generalizing to new situations. For example, if you learned how to ride the bike, your generalizations ability may help you learn how to ride a motorcycle or something like that. And also you got the ability to evaluate alternatives. So, for example, if now I put you in a situation when you have to make a choice, it's your reasoning abilities that will tell you if, for example, a choice is better than the other based on the factors that you have. And we also got the types of reasoning. So we got what we call the deductive reasoning, which is what we use when performing math, for example. For example, when we talked about implications or equivalences, we're mainly talking about deductive because we go from a point A and we get into a point B, for example. Regarding the inductive, it's a bit the opposite, or our ability to generalize. For example, if I tell you that every swan I saw are white, so I assume that all swans are white, for example. This is a type of inductive reasoning. And regarding the abductive, it's our ability to explain what something happened. For example, if I go out and I see that the grass outside is wet, and I will assume that maybe it rained yesterday. And this is a type of abductive reasoning. And so why are we talking about this? Is because we actually want to have systems or models that are able to perform all these types of reasoning for obvious reasons, because it will help us in a bunch of tasks, but also it will get closer to how we as human can think. And so you can ask yourself a question, actually: can LLMs, as they are, reason? And actually the answer is yes. So the LLMs, as they are, or as they are provided, there are many ways to tune them or to use them so that they can perform some sorts of reasoning. And some examples that you might have seen is, for example, in context learning, when you get into your prompt and instead of just asking the LLM to perform a specific task, you give examples of what you want. And it can also it's a sort of few-shot learning when you give so examples of inputs and the outputs that you want. You got also analogical reasoning. It's also the ability of the LLM to generalize. For example, you give some patterns and it generalizes without specifically telling it what it's need to be done. And what we call COT is a chain of thoughts that you also might have seen somewhere. It's basically instead of just prompting the LLM to give a specific response, it gives you a chain of it gives you a response that you then use in another prompt, etc. And also the abilities of LLMs to do some planning. I believe you all used it. For example, if you ask ChatGPT, I want to go somewhere, or I want to travel to this city, build me a plan, for example, and it can build you a very detailed plan that goes step by step, etc. And also, if you're just using an LLM for coding, it also involves some type of reasoning. We can see some of these examples here, for example. Regarding the in-context learning, for example, I asked Quen to translate the following to French. So I gave a couple of examples, and at the end there is "nice to meet you," and the models understand that it has to perform translations, and it just says "ravi de vous rencontrer," which is the equivalent in French. And also here, it is just an example to show what is in-context learning. But of course, if I just, without involving the examples, it would have guessed it as well. But it just to show how it can be done. Regarding analogical reasoning, for example, I asked Quen, bird is to nest as bee is to, and it understands that it's where these animals or insects live, and it guessed that as bee is to hive, and it gives also some explanations that it's for the shelter of the animal. For the chain of thoughts, I have something very basic where I gave the LLM simple problem. So if there are 5 apples and you eat 2, how many are left? So basically it follows a couple of steps and guess the result at the end. And also for the planning, I just asked it to organize a trip to Milan, and it gives all the different steps. For now, of course, there are nothing fancy, and we are still talking about LLMs, and we didn't dive yet into the subject of large reasoning models. And so why would we need another type of models if what we already have do perform what we want? There are actually a lot of problems when we use LLMs for reasoning tasks. Sometimes we have an overconfidence. We didn't see it in these problems, but for example, we can give a math problem. It happens a lot in math when the model has to perform a specific task and it fails, but it doesn't realize that it fails, and it's overconfident in its prediction, and it uses and even continues in the chain of reasoning. But since there is an error at some step, of course, everything will be false. We got also the hallucination. It's a bit related to the overconfidence, but it's basically giving false information or just hallucinate something that isn't existing. And this also happens a lot, and it's quite penalizing when you are dealing with reasoning tasks. You got also the lack of abstraction. So sometimes it is difficult for the model to resonate at a more abstract level. And if you give very simple examples as the ones that we saw, it won't really struggle. But if you give some more abstract problems like maybe puzzles or even problems that involves only language, it can fail to do them correctly. And we also got the fact that the model, after generating something, it isn't really able to verify that what it has generated is true or false. And even, for example, it might have happened to you a lot of times when you talk with ChatGPT, for example, and at some point you ask it, "Are you sure? Maybe this isn't good." And just by mentioning that, it finds that it did some mistake somewhere, and it will correct it. And even now, there are what we call we're introducing the concept of reflection in large language models, so that they can also know what they're generating and maybe reflect on it and maybe refine it before giving the final answer to the result. And also, since the problem of reasoning, it involves generating a lot of steps. When we're having a multi-step, when we are if you failed somewhere, it will cause the whole chain to break. And these LLMs, since they are not very familiar with generating these consistently generating all these steps, so they're not very performant. They're not very reliable when it comes to multi-step planning. All right, so let's move to the next section, where here we will actually learn how to build these reasoning models. So again, why reasoning is hard to learn? So for the reasons that we mentioned earlier, it's the fact that reasoning in its nature is multi-step. So we're not just predicting one output. There is no just a correct answer to generate, as for example, we would do in machine learning in general when you train a model to predict something. Here, it's more about generating a sequence. And this sequence can even not be linear. So you can have parallel paths, or maybe a very complex structure when you got, for example, and even it's what mainly encouraged the emergence of agents, for example, when each one performs something and at some point they also merge, etc. And as I mentioned, also the fact that reasoning in itself is a sequence. If you do an early mistake, it will cause your whole chain to break. There's also the fact that LLMs and how they are being trained, they're not explicitly trained to reason. So when we train an LLM, even if it's in pre-training or in fine-tuning, we're mainly giving it a bunch of data, and we just expect the model to learn how language is built in general. And even in fine-tuning phases, what we're usually giving is, for specific cases, it's more about specific expected output given a specific input. And there is nowhere there is this notion of reasoning or training the model to have thoughts or abstract thoughts. And in fact, this is also due to the fact that how language and how the data that we have is structured. For example, if I want to train, to fine-tune, for example, an LLM to solve math problems, and I got a set of problems in math, but the way that they're structured, I only have the text, for example, the question, and at the end, I just have the final result. And this actually doesn't make it a valuable data for reasoning tasks, because we're just teaching the model that if it has this question, you should answer this. But how? There is no way for the model to just guess it, and it's something very abstract and very complex that we can't even assume that it will just be learned in a latent space or as a feature in its internal weights. And there are also the fact that sometimes just giving, as I said, the final answer isn't enough. Why? Because if we're expecting the model to predict some reasoning chain or some reasoning thoughts, we won't actually to be able to say, in the case of where one step was wrong, which step was actually wrong and caused the model to fail. And this is also, so this is what I wrote here about the need of intermediate feedback. Because if we just expect the last output to guide the model, it can be quite complicated to achieve satisfactory results. So how can we actually teach these language models to reason? So there are actually mainly two techniques which are not which are actually complementary. It's not that we need to use one or another. It's usually they are used both in one order or the other. And the last point regarding self-improving loops, we'll also talk about it in a moment. So let's start with supervised fine-tuning. So we talked earlier about fine-tuning, which is, as I said, fine-tuning the foundation models to perform a specific task. And here the concept is exactly the same, but instead of giving just the output, we're giving the whole reasoning process. And this is what is written here for derivation of trace data. So the reasoning can also be considered as a trace to get into the result. And here what we're so the idea is giving, for example, a question, and we're also giving the whole reasoning sequence alongside the results. And when fine-tuning the foundation model in this, so we saw that the behavior is that it is actually able to behave like that and to perform the reasoning steps itself. So this is a good solution, but it has a lot of limits. So the main challenge for this is the fact that it needs a lot of labeled data, and this compared to other problems, it is quite challenging to get this data, because also the fact that sometimes you need some labeling. And imagine that you have a problem and you have a lot of steps, and each step may be right or wrong. So even if you hire, for example, annotators, it's not just ranking positively or negatively one data point. It's about, for each data point, you have a lot of steps, and maybe one step can be wrong or right, and it can also influence the other. So you can see there are a lot of problems regarding this, regarding the way that we can get data for that. And there's also the fact that when having this data, there is not a notion of success or failures. What does that mean? Is that when it's a bit what I said now. So when you have a whole chain, it's the fact that for each reasoning step, you do not know if this caused success or failure. So imagine that I run a whole chain that has maybe 20 steps, and at the end it gave me a wrong result. So how can I know at which step it went wrong? Because realistically, I will only have the last output, and that's quite difficult to judge based on that. There is also the fact that this architecture, as it is for the supervised fine-tuning, doesn't allow to learn from mistakes. And this is a common problem for supervised learning in general. And there's also the fact that sometimes this technique is overfitting on shortcuts. So maybe in some data points we have some reasoning steps that are not very detailed, and it causes the model to directly jumps to the conclusion. And this is a problem because if we are doing this is mainly to introduce more reasoning thoughts and more reasoning steps to the language models. And if it takes shortcuts, it basically doesn't achieve what we want. But it's still a good solution that gives us satisfactory results, let's say, for very simple tasks, of course. Now let's move to a more interesting technique, and one that is much more used nowadays. So you've probably heard about reinforcement learning in general, and it's a method that is quite used nowadays to train large reasoning models. Why? Basically because it actually gives the possibility for the model to learn from experience, whether was it a positive or negative experience. You can get a feedback not only for the whole sequence, but also for each step. There is also the fact that theoretically, the model can infinitely improve and continuously improve. There is also the fact that by using this method, there are methods to explore different reasoning paths. So if you're familiar with reinforcement learning, it's based on the trade-off between exploration and exploitation, which supervised fine-tuning doesn't provide in itself. And also, reinforcement learning is quite powerful that we can even learn to rank reasoning paths and not just say that this one reasoning path is right or wrong. What is also used, so to get back to this schema at right, so this is a famous diagram that we show to explain reinforcement learning in general. So you got the agent and that interacts with your environment, and based on the action that it takes, it gets a reward, and also done in training, especially. But since in reinforcement learning, we are not just producing one output, but we're rather generating a whole sequence. And sometimes, most of the techniques, what they're doing is that there are some algorithms to kind of simulate how our agent will behave in a particular situation. And in order to do that, it kind of needs what we call a model. And a model in the context of reinforcement learning, it can be just a function, for example, that will tell you when you are in that state, and if you perform that action, you will expect this type of reward. And this is quite helpful, as I said, because when you're what we call bootstrapping is basically you're assuming that you might be in a situation and what will taking this action would imply. You won't really have the possibility to try it then in your environment. It's a bit similar to you when you are thinking about doing something, for example, and you will assume what will be the consequences of doing this thing. And you will learn from that instead of putting in real life your situation there and getting a real life feedback, let's say. And so to get back to our subject, so because here our agent, as you might have understood it, is our large reasoning models. And so researchers introduced, it's actually engineers from OpenAI, they introduced two concepts. One is called outcome reward model, and the other one is process reward model. And so these reward models you can see them as functions, but in fact they're even neural networks that takes for the outcome reward models, that they take the whole sequence and they give you an estimation about the reward that you would expect if you perform these actions in your environment. And for the process reward model, it's the same thing, but it is at the step level. So you don't need to give the whole sequence. You just need to give a step, and it can be viewed as a function that will tell you, being here, you would expect that amount, that average reward, let's say. And so this will be we'll also see this in the next section, how it can be used in the inference. But to summarize a bit, how reinforcement learning can be used in training large reasoning models. For example, here you got an example when you give simple question and you tune your model to perform some reasoning, and at the end you have an answer. And let's say that here you have a reward model that can be trained or not, that you can train in that phase or in the previous phase. And so this reward model can give you an output about the expected reward. And why is this helpful? It's because at inference, if you want to perform this, you won't need to get the feedback from the environment. Because in fact, in inference, you won't have an environment to get the feedback from. So, and to spoil a bit things, we'll see later how DeepSeek is built, and it's mainly based on this technique. So for just having a reward model, and at the end, so you get also an error signal. Basically, it might be it's just a reward signal that tells you how good your answer is, and you iteratively fine tune your model so that it can output the best answers at the end. Regarding outcome reward model, it's a bit similar, but here we mainly also track the different steps that have been done. And once we have the outcome at the end, so we have the outcome reward model that will also predict a reward based on our answer. And this reward will be used to fine-tune the model, but it will also take into consideration that our model produced these steps in the workflow. And concerning process reward model, so here we'll get a reward for each step. And so here at the end, so what will happen is that when we generate a question, for example, we can get a value of an estimated reward at each stage. So if we're at this stage, we'll get for a question many possibilities, and we can actually learn that this output, for example, is the candidate that will probably give us the best result. So it will be a bit clear why these two types of models are helpful during inference time. There is a last concept that is quite interesting, which is about self-improving loops. So here, let's say that we now trained our large reasoning model so that it can perform, so it can produce good reasoning steps. And then we also have the process reward models, for example. What we can do is actually use this PRM model that we train to select what are the best reasoning steps, what are the best reasoning paths. Let's say, for example, concretely, I have a huge data set of a lot of problems, and so I just run these questions, for example, through my LLM, and I get a lot of branches for each example. And because I have my PRM, I can rank the quality, or I can assess the quality of each reasoning branch. And at the end, I can get a set of reasoning paths and a set of, it will be couples of questions and reasoning paths that can be used to fine-tune my foundation model that I have. So it will give you something like that. It is this concept is actually implemented in the OpenR framework. And so it's basically you have your LLM that is acting as a policy, and you are generating a lot of data. And because you have your PRM, you can value the quality of this data that you have generated. And then you can fine tune your model on this. And this created a huge whole topic in itself in large language models in general. It is an area now called self-improving foundation models, and its goal is really to be able to have language models that can self-improve without additional knowledge from human. And when it comes to inference, it will just act with guided search and planning, as we will see it in the next section. So now we'll discuss how we can use, and we'll discuss what is happening during inference. Because if you're using, as I said, you're probably using now large reasoning models when you're chatting with ChatGPT, you might have noticed that it takes some time in the beginning to perform. So it will write you something like thinking. If you're using DeepSeek, it's the same. You will see a reasoning section that will pop, and in this section we'll see what is really happening in this kind of models. So it's called test time scaling because there is a theory of that we can actually scale the quality of the answers by taking more time to answer. So there is a trade-off. If you take more time to think, you will get better results. And why is this an important topic? Because theoretically, we can actually improve the quality of our results by improving the reasoning without additional training, because we're now at inference time. And as you remember, there's no training at inference. We can also encourage better thoughts and more structured thoughts without also giving more data into this. And as we mainly saw, the accuracy on this type of problem is usually directly related to the ability of the quality of the reasoning. So there is a direct correlation between the reasoning thoughts that the model will do and the answer that it will output at the end. And so to do this, basically what will happen, so let's say that you got this query and you give it to the large reasoning model that you just trained. So what it will do, it will generate usually multiple paths, and then it will kind of go through all the steps and choose, and this it will differ on the technique, and it will at the end gives you a response based on the method that it uses. For example, for majority vote, so you give a query, you give a question, and it will generate, as I said, a lot of reasoning paths, which are usually different. And what it will do is that it will see that two of them may give you the same answer, and it will say that it will assume that this output, since it has been generated more often, it is the best, it is the true value, for example. And by using this, so as you can see, so it can take maybe 10 or 20 or maybe sometimes 200 times more time to generate, because some models, I guess, like DeepSeek can run into 100 or 1,000 parallel paths for each query. And the end, so we can just perform, as I said, so this technique is called majority voting, which is about sampling the output that has been sampled the most. Regarding tree search, it can be, for example, a technique that is more greedy. For example, if you have multiple paths, as here, you can use, for example, if you have a PRM here, you can use it, or just use the confidence of the model and sample the step that has the highest accuracy or the highest confidence score from your model. And if you can follow through this, you will get to the answer that you consider be the best. Regarding beam search, it's a bit the same as tree search, just that you can take more paths as candidate paths, and at the end you can end up with you can end up in a node that has a better confidence score at the end. You can sample this at the end. And what is quite interesting, and what is linked a bit to the previous sections about ORM and PRM, is what we call look-ahead search. So here, the process will begin in the same way. So we have a query, we have a lot of parallel paths, and what we'll actually do is we will select the path that we'll select the path that we'll consider is the best based on the value of the PRM. So again, to repeat, the PRMs will assign a value at each step, for example, and the highest, or if the PRM considers a step that is more likely to perform the addressed query, so it will assign to it a higher score. And so for the look-ahead search, it will say that it will use this score outputted to select the path to explore. So instead of doing the whole process of going through all the different paths, which can be quite expensive, so you can see this as a method to cut down also the inference cost. And so there are actually quite a few PRM-based technique so to perform the inference. Because, for example, the best of n. So for here, we do the whole process. We have a question. We got a lot of parallel reasoning paths. And at the end, we use the PRM to give a score for each path. And we'll just keep the one that gave the best score by the PRM. You can do this at the step level. So instead of generating all these reasoning paths, you will also only select the one that has the highest score by the PRM, and then redo this. So you will generate the next steps for another level, and at each time you will just pick the one that gave the best PRM score. You can also perform beam search. So beam search, again, you keep more than the best answer that your model predicted. You can keep, for example, the two best, for example, here in this technique. And at each time you keep the two best, and at the last layer you keep the best one, for example. And there's also another method called beam annealing search, and this just reduces the degree of the beam at each step. So we begin with 3, for example, and then 2, and then 1. So I know this can seem a bit abstract, but hopefully this will get a bit more clear with this example. So let's give the following question. You have, I don't think it's worth it to go through the whole problem, but you just understand that it's a math problem. You have some choices to do. You have some information about this figure, and you will ask your large reasoning models this question. So what it will do at first, it will generate different maybe methods or strategies to solve the problem, or it will just begin analyzing how it is. And what you will have here, so based on this, we'll get these answers. And what you will see here is the score outputted by the PRM. And here, for example, for this step, you can see that this has the lowest score by 0.2, and all the others has higher scores. And so what we'll do, we'll eliminate this branch and keep all the others and perform the same step here. So we'll get also other values for the PRM. And at each step, we will discard the one that with the least score. So this is for the beam annealing search, but you can use a more greedy strategy if you want. If you used, for example, here this method for the step level best of n, which can be considered a greedy technique, we'll mainly select, for example, this branch, and we'll discard all the others, and then select this branch, etc., until getting this one. And this might not be the best thing, because let's assume that this one is the one that gave the best results. And if we discard this, we can see that in the next steps, we get a much higher PRM score here. And it is quite common also in reinforcement learning. When you're using a reward model, it will be more accurate when you get closer to the end of the sequence. So this is a bit for how PRMs can be used for inference tasks. But of course, this isn't mandatory, and it isn't what makes large reasoning models. So as I said, we will see later in DeepSeek, they didn't use LRMs nor PRMs, but it still worked quite good. You get also another example that is quite interesting. It's called the REACT framework, REACT for reasoning and acting. And this is so interesting that you can even maybe implement this maybe using prompt engineering if you design carefully your prompt. Let's say here, for example, I got a question. Aside from the Apple remote, what other device can control the program Apple remote was originally designed to interact with? So if we use a standard LLM, we can get a direct answer like iPod, which is a false answer. If we rather use chain of thoughts or reason only, so this is how the model will behave. So it will start thinking or it will assume that it is thinking, and it will here it's mainly an hallucination with all outputted here, and it is false. And the end, it will generate all these, which are false results. If we rather use act only, so act here is performing action, and to perform actions, you usually need tools. One of the most used tools, and it's the search tool, which can be, for example, linked to Google in order to get the result that you want, or maybe just a knowledge graph that you have, or a database. And you will just, it will have a certain structure to interact with your tool. For example, you have search, and you can mention what you want to search and then get the results in form of observations. And so for the act only, what they try to do is just perform actions and observations, and they will, at the end, it will try to output here, even the answer is not even related to the question. But here, moving to React. So React, what it does, it has 3 steps. It has the thought, it will think about what it should do, and then it will act. It will act, performs an action with the tools, and then analyze the output of the action so that it can perform next actions. So for example, here, it says that I need to search Apple Remote and find the program it was originally designed to interact with. So it will perform the action of search Apple Remote, and then it will get an observation based on this search. And so based on this observation, it will also analyze it. So it will say, Apple Remote was originally designed to control, blah, blah, blah. I need to search front row next and find what other devices can control it. So now it has some another data. So it search front row. And here, something interesting that cannot be done in the previous frameworks. It will get this observation. We could not find any information about front row, but we'll get maybe similar. You may be talking about front row seat to earth or motorsports or software. It will understand that it is looking for the software. So front row is not found. I need to search front row software, etc. So it will perform another action, just search, and get an observation, etc. And then at the end, it will get the final thought. Front row software is controlled by an Apple remote or the keyboard function keys. So the answer is keyboard function keys. And there you get the result. So it's quite powerful framework, and it can perform quite well the whole process of reasoning in itself. And as you can see it's quite also interactive in terms of you got tools, you can interact with the tools and also analyze these tools, and not just thinking of how something can be, as it is done here, for example, in chain of thoughts, and it gives you quite good results. An interesting thing that I mentioned earlier regarding the test time scaling law. So there is an investigation that has been done by researchers from DeepMind, and they actually compared different architectures, especially regarding large reasoning models, and they tried to prompt them and to train them using different methods. And something quite interesting that they found is that sometimes you can rely on models that are maybe 4 times smaller, and that will perform better the task. If you have a reasoning model that is 4 times smaller than a large language model, for example, they can achieve, your large reasoning model can achieve the same or maybe better results. It is shown in this graph. So I know there is a lot of information here, but if you follow the best of n weighted, here the orange line, which is considered by the authors of the paper as the baseline for the LLM. And for example, if you take the blue one, which is a large reasoning model that has been trained and that is been inferred using beam search, you can see that the model can be 2 times smaller and still actually perform quite well, or maybe here better than how the LLM is performing. And so this is one scaling law. It is the accuracy regarding the size of the model. but there are also others regarding the data, because here, if you're aware, we are actually running out of data. We are training the language models with all the data that we have, and they are no longer improving. So maybe if you followed, if you didn't hear a lot about Llama 4, for example, it's because they kind of reached a plateau and they are not getting better results that they already have. And so this actually poses an important challenge, because where can we find more data? And one of the solutions that has been proposed is what we talked about earlier regarding self-improving foundation models. And this might actually be the way to get actually more data, because it's not hard to generate a lot of synthetic data, but what is actually hard is how can we generate high quality synthetic data that can be so good that training our foundation models on them will cause models to improve. So this is a whole research area. You can there are a lot of resources online, and you can catch up quite easily. All right, so now let's move to the interesting part of the presentation. So as I said, you've probably heard about DeepSeek and how it caused a huge sink in NVIDIA stock, for example. And you might actually be able to understand how it even caused that. So DeepSeek. So before diving into DeepSeek, let's do some recap on reinforcement learning. So these few slides can be a bit technical. There might be some math on it, but if you cannot understand, don't worry, it's fine, because we will explain again the concepts, and you can still understand why or how they could achieve such performances on it. So to get back to reinforcement learning in the context of training large reasoning models. So in RL we principally have the policy, and the policy, what it is, it's basically you can see it as the function that will tell you which action to take when you are at a particular state. So here the state, for example, is the prompt that is given, and also maybe the text that has been already generated. So you can define this as a state. And so this policy, which is here, of course, the LLM, will actually sample the token that is more likely to give the best results. So here, this is what we will call the policy. And in reinforcement learning, we also have the reward model. So here it's basically, so we talked about about models earlier in ORM and PRM, and this is also the same. It's just a function that when you give it the whole sequence of steps that you've done, it will give you an estimation of the reward that you would get in the environment. And the last thing that we have, it's not common to all reinforcement learning architectures, but in most of them, we have what we call a critic. And a critic is also a function that will actually tell you how much reward can you expect while being in on a specific state. So this so you can maybe follow more reinforcement learning lectures in order to dive deeper into all these things. But if you can follow at this stage, it's actually great. So here, how reinforcement learning is actually used in reasoning models. So the first step is to generate the responses. So the LLM will give in the prompt or the question, and it generates multiple responses. And what we want to do is to be able to give a score to each one of these responses. And for that, we'll use the reward model. And for each response, we'll assign a reward. And what we'll do is that we'll compute what we call advantages. And because reinforcement learning, the goal is to maximize the advantage. And the advantage, what it is, you can see it as the improvement. How much, how improved will our model will be if it only generates this method instead of the others. And so this is called the advantage, and we'll see it in the next slides. And at the end, what we want to do is to optimize the policy. So as I said, the policy is the function that will choose which action to perform, or here more concretely, which token to generate or which step to generate. And the goal here is to optimize the policy so that it maximizes the advantage. And also what we want to do is to update the critic. So because the critic, it goes alongside the policy, and the critic should be aware of how good is our policy, and it will be good at estimating what can we get from following a specific policy while being on a certain step. So let's dive deeper into the general advantage estimation. So how can we define how improved will our model be? It's basically what we'll do is we got the expected cumulative reward of taking a specific action. So let's say that we are at the state ST, and we want to know how beneficial would it be for us to take the action AT. So we'll basically need to compute this. So it can be seen as how much reward would we get by performing this action, and we'll compare it to what is the average reward that we actually get while being on this state. And this is the advantage. So at the end, the intuition behind that is that if you perform an action that is worse than the average action, it will cause this advantage to be negative. But if your action is something that will give you an expected reward that is superior to the expected cumulative reward, so the advantage will be positive. And by updating our policy to optimize this advantage, we'll make our model to choose the best actions at the end. But concretely, it's quite difficult to do all this because if we want very accurate cumulative reward for a specific action, what we want to do is that we need to bootstrap all the way around until the end so that we can get to the reward, and then assume that if taking this action is beneficial or not. And if we are evaluating this for every action, so it's quite kind of equivalent of going through every single node in the tree. And of course, this is not feasible, especially if we're relying on a huge architecture like LLMs. It won't be feasible to sample everything. But hopefully, the RL guys gave us another technique, which is called temporal differentiation learning. And basically what you would do is that instead of going through the whole node, you will just compare what you would get at a specific state compared to what you get at the next step if you take the action. And it's basically just leveraging the power of the critic, and it will assume that the critic will know if by taking a specific action it will give you better results or not. So at the end, you will end up with something like this. So this is simplification of the true method and of the true formula. And so you get at the end the average general advantages estimation. And this is what will be used to fine-tune the model, or this will be the objective of our model. And so here, this objective that is given is for a PPO. So you have the objective that is here. So you get a clipped version of the advantage. Why clipped? It's because we want the training to be stable. And so by doing so, we avoid having high discrepancy in the gradient and then making our model more stable in general. And at the end, when this is our final objective function that we are optimizing in PPO, we got the reward. So this is, we want to maximize the advantage, or it's basically we want to maximize the ability of our model to choose the best action. We also want to maximize entropy. So here it's for having a diverse set of answers, because if your model is too greedy and only samples one single thing, its entropy will be much lower, but we actually want to maximize it so that we can allow our model to explore more. We want to penalize KL divergence. So this is for the last and the new policy. And it's also another method to stabilize the training. So we're basically making sure that the policy doesn't change too much, because it can cause a lot of problems and it can end up diverging instead of converging. And at the end, we also want to minimize the loss function of our critic. So, because don't forget that we're also training the critic along the way. So this basically to say that we're also training the critic. And so this is for PPO, but in fact, it's not what is being used in DeepSeek, but it's quite important to understand how PPO is made, to understand how GRPO is, because GRPO is the method that is actually being used, and it's actually much simpler than PPO, because how does the workflow goes? So you got a prompt, you generate a set of responses from the policy, and what you will want to do is to generate rewards, compute rewards for each one of the responses. And at the end, so you will, based on these rewards, you will compute the advantage. And how you will compute the advantage is basically by comparing the reward that you get from the different responses. And it will give you something much simpler. So you just comparing your reward to the average reward. And even your loss function for the GRPO, it will involve only maximizing the reward that you got here from the advantages, and penalizing the child divergence. So you may ask, where are the other terms that we have here? And in fact, we do not need to maximize entropy by doing this, because in itself, by generating a lot of responses, we are encouraging the model to explore more. And so we're kind of brute forcing the exploration here, compared to the first method where there was a risk where we get stuck at a path that we only sample again and again. And another parameter that disappeared is the critic, because if you see here, the advantage, we're not using anymore the critic to compute the advantage. It's just by computing the reward and comparing it to the other rewards. So the whole critic just disappeared from our system. And by doing that, we can actually, it's what gets all the benefits of GRPO. It's, as I said, the fact that we do not actually need a critic, because a critic, it's still a non-deterministic function. It's just an estimator of how good our model would be. So it adds a sort of heuristic to our system that we do not actually need. As I said, there is the fact that we're automatically exploring, and we do not actually need to force our model to explore more by, for example, trying to maximize entropy, which can, in fact, cause the objective to be a bit conflicting, and because it will transform the problem into a multi-objective, which can make it much harder for the model to focus on the main task of maximizing advantage. There is also the fact that the computations are actually much, much more efficient. So as you saw it earlier for when we're relying on, if we perform MCTS or TD learning, you can see that you kind of have to generate a lot of different paths and compute the rewards based on that. And but this just relies on the rewards and how good the reward is compared to the others. And what is usually done here for each inference, for the training at least, I believe they sampled around the thousands of possible responses, and that's what makes it a good estimator, because even in the first papers of reinforcement learning that has been proposed to do that for the advantage, what you need to compare is you compare the actual reward that you get with a baseline, and the baseline should be a good estimator of the average action. And here it's just the idea behind GRPO is that we already sampled an important set of paths or an important set of candidates, which makes the mean here a good estimator. And that's what makes it actually quite efficient. And at the end, it's also quite, it's not very heavy to compute all that. So it's all win. Here you got an architecture. So if you didn't follow all the maths or you got lost somewhere, maybe this visualization can help you more. So here for the PPO, you got here, as I said, the policy. So you got the output. And from the output, you will get the reward. So based on your reward model, you will actually get an estimation of a reward, but you will also get the value based on your critic. And this value and the reward can be used to compute the advantage. And this advantage is basically used to give you the answer, and then you just update your policy in order to improve this advantage. So that's basically it. But compared to that, GRPO, what it does is that based on the policy, you will actually generate a lot of outputs compared to the PPO, where you only generate one at a time. And you will actually, here, as you can see, the value or the critic is no longer necessary. You just have a set of outputs and you compute the rewards. And based on that, you compute the advantage for each output and for each reward. And you just update your policy to maximize all this advantage. Some other specificities regarding DeepSeek R1. So regarding the reward, because we talked a lot about the reward model, but we didn't really define how it is. And because in general, it's not necessary that it is a neural network that is trained on that. For DeepSeek, they did something very simple. They discarded all PRM or ORMs, and they just used deterministic rewards. And it just binary checks. If the answer is correct, the last answer is correct, we output 1, else we output 0, just like that. And they also they also included in the reward the fact that they follow a certain type of formatting. So this is a bit similar to the React framework that we saw earlier, where we actually force in the model to have some think in phases and then answer in phases. And this is also quite useful to parse in the developer side also. They also included in the reward the language consistency, because I guess they had some problems sometimes when prompting the model in Chinese, it performs the thought process in English. And so they introduces this constraint to force the model to be consistent in one language. And so why did they use that? Is to avoid a problem that is called reward hacking. And it's a bit related to the fact that models sometimes take shortcuts. And if your reward model is also non-deterministic, if it's a neural network, for example, there are high probability that if you give a step that isn't really the one that you need, you will still get maybe a high reward estimation. And to avoid this problem, they just said, all right, let's build something dumb. Let's build something deterministic. If it's correct, we give the point. If not, we do not. And just by doing that, it worked. Another interesting insight about DeepSeek, the fact that they actually, it's what we call, they began with a cold model without initializing. Because if you compare it to how OpenAI GPT-4o1 model is built, there usually is a huge supervised fine-tuning phase in the beginning. And then we move into an online method where we involve reinforcement learning. But DeepSeek, they didn't do that. So they actually did some supervised fine-tuning, but it's with very few examples. And the goal for that is just to initialize or to show the foundational model the format that it needs. For example, to follow the steps, etc., and to add the formatting, for example, regarding the think and the answer formatting with the And actually, because this actually also helped a lot reducing the cost of training, because self-supervised fine-tuning is quite expensive and quite heavy to do. But by doing this on only a few data points, it actually helped them save a lot of cost and a lot of time. And why also supervised fine-tuning is quite useful, even if you know that you will have a reinforcement learning phase later, is that you want actually good starting points. And because, of course, as any objective that you would like to optimize, sometimes it just depends on the starting points that you have in your model. Another thing that they implemented is the fact that after doing the training with reinforcement learning, they generated 600,000 reasoning trajectories. And what they did is that they filtered out the responses that were incorrect. And after that, they fine-tuned again the model on these correct answers. So it's a bit like they wanted to additionally fine-tune the model to output very high quality reasoning steps, etc. And after that, because as you may have seen, so DeepSeek, they came with a bunch of models. And even I believe the one that is available on their website, it might not be the R1, or by default it isn't. And so how they build these smaller models, they did a concept known as distillation, where you actually have a teacher model and a student model, and you basically train the student model to behave like the teacher. And how did they do that? It wasn't by doing some fancy architecture. It by training the model from the outputs of the R1 model. So it's something very, very simple. And it actually worked. It wasn't over-engineered, it wasn't complicated, and it gave actually quite good results. Let's end up with another example. This isn't the DeepSeek R1, but it's another model inspired by DeepSeek. It's called Search R1, and it includes the use of tools in large reasoning models. So, for example, they gave a question: where are Teide National Park and Garahone National Park located? So the expected ground truth should be Canary Islands, Spain. So the model will start thinking, I need to find out where Teide National Park and Garahone Park are located. So it will perform a search. So it's a bit similar to the React framework that we saw earlier, just that it is more trained in a DeepSeek way, regarding, as you can see here, the tags for the thing, and they added actually the search and the information. And you can see that it performs quite good, because you got the search and you got the information that is retrieved using their search engine. And based on that, they also do some thinking, some searching, etc. And so what they have done here is just that they trained also the model to interact with the tools, and they taught it how to retrieve tools and also how to use the tools that you have. And I believe this is a quite interesting direction, and especially if you're working on any application that works with the LLM, you can at least simulate this quite easily. So it's definitely something that you should look to. So now let's move to the last section of the presentation. What are some challenges and limitations of large reasoning models? So first of all, we have the problems that are related on LLMs themselves. So LLMs are made to predict and are not meant to present. They're basically predicting the token that is most likely to be predicted in a sequence at each step. And they're not meant in their nature to do reasoning. There is also, of course, the fact of hallucination, as we saw it in previous examples. And there is also a problem of poor generalization. So the model sucks at generalizing most of the cases. There's also another problem. We talked about it earlier. It can be defined as the domino effect, where if you got errors, especially at early stages, it will break the whole reasoning chain. And there is also this example. If you got, for example, a model that has 90% accuracy and you have a chain of 20 steps, the accuracy of your whole system is only 12% because you kind of multiply the probability of making an error at each step, and at the end, you have a much lower probability of getting a good answer. And this is actually quite common in practice. When you try these models, you can see that they are not as good as we expect them to be. There's also the problem of credit assignment. So when you have a chain and it breaks, and when you get a wrong result, it's often difficult to tell at which step the reasoning broke, or which step were actually caused the chain to break. There's also, as we talked about, the test time scaling. So it comes with a huge drawback, is the fact that we are thinking more. That means that we're generating more tokens, and we're also doing much more computations. And especially if we start running multiple reasoning branches, like if we do tree of thoughts or beam search or any other method, we are actually multiplying the cost and also the time, sometimes even to 100 with a 100 factor, which might not be acceptable in a lot of use cases. There's also the fact that it's still hard to evaluate what a good reasoning is, even if you bring some human evaluators. It's actually difficult to generalize the fact that this reasoning is good or this reasoning is better than the other. So it kind of adds another challenge. There's also another interesting point. So this paper came out very recently, I guess a week ago. It's called Proof or Bluff, and basically they evaluated LLMs, but it's actually they evaluated large reasoning models on the latest USA Math Olympiad, and they actually an interesting result, because they saw that the models were terrible at these tasks compared to previous Olympiad, and they actually assumed that most of the models that we have are actually overfitted on a lot of benchmarks. So it's a recall to everyone to not trust every benchmark you can see, even from papers published by top companies. And this is maybe a more concrete example. You can see that for the latest Math Olympiad, so they actually tested the best models that we have, actually, from Gemini to DeepSeek R1 to OpenAI, etc. And you can see that apart from Gemini that scored 10 over 40, all the others scored 2 or below. So they got very terrible results. And if you compare it to the 2024, for example, Olympiad, you can see that the results were much better, but without it wasn't that this test is more difficult than the other. It's just that these foundation models have been trained on previous tasks, and then they might actually be overfitted. And this actually raises a lot of discussions that can even be related to large language models themselves. Are they the way to build more sustainable or more robust reasoning models? And actually, the answer might actually be no. You got a lot of scientists that are suggesting moving out from LLMs. You get, for example, Yann Lequin with his new architecture with the GEPA. You may want to have a look on it, for example. And you got also a whole field called neurosymbolic AI, which is aiming to combine more logical, more concepts that are related to logic into AI in general, and even in the context of of text generation, etc. It is they're quite active in this field, and it might be the way to go actually. So that's it for me. I hope you enjoyed the presentation. I hope you could learn from it. And don't hesitate if you have any question, or if you want more clarification, or if you just want some resources to dive deeper into one of these areas, feel free to contact me and I'll be happy to help.
Like enlightening topic. It was so great, very detailed, mashallah. يعطيك الصحة. So we're gonna take a couple of questions before we end. And the first question says, you have mentioned already those limitations concerning the LLM architectures. You mentioned one of the solutions is building new architectures, maybe approaching with like those neurosymbolic approaches. My question concerns are bio-inspired neural networks or maybe neuroscience. Latest discoveries on how human brains function. Those insights from such science are shaping such kind of development of reasoning in modern LLMs?
I guess the answer would be yes, because there are surely people that are being inspired. But there is actually a lesson that we can learn from the DeepSeek example, is that over-engineering is not always the best solution. Because even for a lot of concepts that I introduced, for example, the ORM and PRMs, etc., there are actually what can be considered a biased solution, where we introduce bias in the solution because we assume that if it works well in human brain, for example, it should work well in this use case. And by doing this, we introduce a bias. And this assumption may not be true because the two architectures can be quite different. So I would assume that we will probably get a lot of insights from bio-inspired neural networks, but maybe we can move out from the LLM sphere. And that's what I think it will bring a lot of interesting paths in the future.
Okay, thank you for the answer. And also, there is like another question that it says, we know that LLMs, which are transformer-based architectures, they are not only like limited to as you have said, bias to the data, and also like they cost in time in training or or post training. So there is new approach which is like those past architectures, LSTM. We now have XLSTM, Mamba, and now also like we have hybrid models that combine between Mamba and transformers. And my question says, are there already benchmarks or tests that were done on such architectures, and are they performing well?
It will depend. They might have been. I do not really know for the specific architecture that you mentioned. But for most of the concept, at least that have been introduced, for at least what I defined here as large reasoning models, they were trying to leverage what we already have using language models, with large language models, with the foundation models that we have. How can we go from this into models that can also do reasoning? And so before going that with the architectures that you mentioned, there might be steps that we should do before, and maybe reach the LLM level in a lot of steps, and then go beyond this. And so there might be works that are that are related to reasoning models with these architectures, but I believe can find out. Yeah.
Okay, thank you. And another question that it says, I've seen a paper, like I forget its name, but it concerned tokenization. And like they created a new algorithm. It's like a new approach based on that famous tokenization optimization algorithm. I also forgot its name, but like they have leveraged certain languages to improve the accuracy of the LLM that they trained using that new tokenizer. And also, like as we say, LLMs, as they see language, they see them as like discrete, as if it was a discrete language with different tokens. So, are there like research, maybe approaches or like directions that work on how to represent language, not maybe as discrete approach, as for instance, discrete approach does not work for continuous manifolds such as real numbers. Yeah, that's my question.
I believe the paper that you're talking about is by Meta regarding the concept. I do not recall the name, but it's basically moving from tokenization into concepts. So we have a set of tokens, and regardless of the language that you're using, you are defining a sort of concept and all the operations that will be regarding these concepts. And it's like learning the concepts automatically when given a lot of data and then moving. I believe this also falls under the category outside of the category of LLMs, because even I do not think that the method that they're considered is, especially when we talk about optimization and modifications at an architecture level in the transformer stack, we're moving out of LLMs, and we can actually, and I believe this is the way to go. We shouldn't be just focused on what we can achieve with LLMs, but I believe we can achieve much more with different architectures, and I believe it's quite promising method that they introduced, and I believe it is quite related to what I told earlier about what Yann Lequin wants to achieve in the GEPA architecture, where you actually get joint embeddings and all the computations are made abstractly and not at the token level, as you said, or at any other level. So I personally believe that is the way that we should explore, and it will probably be the future in this domain. Yeah.
This was the last question. So once again, thank you very much for hosting today's talk, and it's our pleasure to have you with us. And yeah, thank you everyone for coming to today's session. See you, inshallah, tomorrow for a topic that concerns AI and cybersecurity.
Thanks. See you.